Okay, this is a simulation of the motions of the sun and the moon in the sky. Here the yellow dot represents the sun and the white dot represents the moon. And the Earth in this simulation is a flat disk and the sky is a sphere. This is the apparent view of the Earth and sky if you just walked outside and looked up. It's also the view of the universe that was taken literally by all ancient cultures. We know today that these bodies in the sky are at very different distances, and yet they all appear to be projected onto this sphere. Okay, let's look at the motions now if we were just to speed up the actual sky. What we see is the sun and the moon each circling the sky approximately parallel to this blue circle here. And this blue circle is the celestial equator. Whenever you spin a sphere, you're going to have 2 points that are fixed. So this is the North Celestial Pole, and that's the location of Polaris, or the North Star. Here's the South Celestial Pole. And so what we're seeing is the dominant movement is the spinning of the Earth. That happens once a day. The yellow line, or the yellow curve here, represents the path of the sun through the stars. And the sun moves along this curve, but it takes a year. And so I would have to spin this model 365 times for the sun to go once around this path. The moon is on this white curve, and that takes a month to go around. And so I'd have to spin this model about 29 or 30 times to get the moon to go all the way around. Now, the way things are lined up right now, notice that the path of the sun and the moon cross at this point. This new moon would actually be a solar eclipse because you have a precise alignment. If I move the sun a little bit away from this place where the two orbits cross, notice that they are still in alignment, generally speaking. That would still be considered new moon, but you would not have an eclipse. So eclipses occur only on these two occasions where the two orbital paths cross. We can approximate the moon's orbit with the sun's orbit, and let's do that for a minute, and then we'll come back to the full details afterwards. So if I just cancel out the tilt, I brought the two orbits into alignment. And let's look at a few things this way, and then we'll reintroduce this extra complication. Let's run it for a day just to separate the two bodies there. Okay. The purpose of this little exercise is to see how the motions of the sun and the moon would be observed at Serpent Mound. This is a site in southern Ohio built by an ancient Indian culture. And let's see what happens here with the rise and set times. I'm going to put the season here to summer solstice, and I'm going to put the phase of the moon to full, so the sun and the moon are opposite, and let's run it until we get to moonrise. Okay, here's the moon rising, here's the sun setting, and notice where the moon appears to be, namely right in this bend of the serpent's body, the southernmost bend of the serpent's body. And here's the path of the sun and moon as we've collapsed them together. And notice we have essentially perfect alignment with this bend of the serpent's body here. Let's move the season to vernal equinox, and let's again go till moonrise. And there we go. Here it lines up at the middle bend of the serpent's body. And let's go to winter solstice when the sun is furthest south, but the moon is opposite, remember, and so that's going to be furthest north. So winter solstice, and let's go to moonrise. And notice that if we line it up with this observer, it lines up over the midpoint of this arc over here. Okay. Now let's come back to summer solstice. We're going to focus on that one most of all. So I'm going to go to summer solstice, and that's when the moon should rise over here. And let's let it run. Okay. Now, what we want to do is reintroduce the fact that the moon's orbit is different from the sun's orbit, because this is not realistic. This is the ideal case. We could say that accounts for these 3 points here. Those points would be the rise points for the ideal full moon at summer solstice, winter solstice, and the 2 equinoxes. Let's put the tilt of the moon's orbit back into the picture. And so here's the moon's orbit. And notice that at this particular time, the moon's orbit and the ideal orbit, which is the ecliptic here, look pretty closely aligned. But let's step it a year at a time. And notice that if I change it a year at a time, it turns out that the direction of tilt of the moon's orbit varies. And where that orbit intersects the ground wobbles back and forth the full width of this bend of the Serpent's body. Let's back up and see this in a different perspective here. So here is 1 year at a time. You can see that the moon's orbit is always tilted 5 degrees, roughly 5 degrees from the ecliptic, but which direction the tilt occurs is something that cycles, and it's an 18-year period, roughly 18.6, I believe. Let's go back in and see how this manifests itself. So if I take this to the max to the left here, this is the furthest north moonrise position. In fact, let's just run it around to moonrise. So this would be the minimum southern moonrise, if you can think of it that way. Some of the other diagrams for Serpent Mound speak in these terms. And if I go to the other extreme, and then let's also go to moonrise. There we go. Here is the maximum southern moonrise. And notice how well that matches the width of this bend in the body. Okay. Let's step it a year at a time. So if I go from here 0, if I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, and here's 19. It's 18.6 actually, would be the years to cycle in this way. So the moon's orbital tilt cycles around the ecliptic every 18.6 years. That variation in the tilt, by the way, that wobble, is called the precession of the moon's orbit. Okay. So this was the first thing that caught my attention when I started this project. When I first met Constance, by the way, she said, "Can you calculate moon rises and alignments for Serpent Mound?" And I said, I don't think ancient cultures could do that sort of thing because the moon has such a complicated orbit. And it took me a while to wrap my head around it, but I realized finally that the moon in general does have a very complicated pattern of rise positions along the horizon, but if you focus only on the full moons, we have this simplicity that it's directly across from the sun, plus or minus a little margin of error. Let's move next to the sunset at summer solstice, which is another alignment found at Serpent Mound. But to do that, we're going to have to move our little figure up here to the head of the serpent. So here goes. There we are. So I've just moved our figure to this little V point in the head, and there's an alignment from here through the, and if you consider this to be an egg or whatever else this might be, this oval in front of the serpent's head, this alignment appears to be to the sunset at summer solstice. Let's see how that works out. I'm going to change the season to summer solstice, and I'm going to set it so it'll stop at sunset, and let's let it run. And there we go. Now let's see what this alignment looks like. And if I zoom in, there we are. and the alignment is close but not perfect. And we're ignoring the moon right now, so we don't even have to worry about the white one. But the sun itself, notice that as it's setting, it's a little bit to the right, a little bit to the north of this alignment. This is easier to see, actually, if we turn it around, look from the other direction. So here's sort of an artificial way. We're beyond the sky, looking back at here. But notice here's the alignment, and at summer solstice, we're beyond the alignment. Now, this model is not a perfect sunset calculator because, first of all, this sun is an artificial size. It's not the size of the actual sun. Where the sun is at sunset is when the last gleam of sunlight blinks out, and that would be considered typically to be the sunset point. There's been some messing around with that definition by other researchers because they're perplexed by this misalignment, and they're looking for possible explanations of why it's misaligned. So they thought, well, maybe they used other definitions. But if we stick with the traditional definition, when the sun blinks out is the most obvious, to me at least, that seems to be the most obvious event that you could record. It definitely is misaligned. And this is about a degree and a half. And so this point, it turns out, is about 2 weeks prior and 2 weeks after. This is an interesting offset because even though this might be the summer solstice, the moon might not be at full moon. We can artificially put this at full moon so you can see where the full moon rises when the summer solstice sun is setting. But the moon could be in any phase at this particular solstice day. And so we might have to account for the moon being a little bit earlier or a little bit later when it gets to be full. So what we're looking for is the full moon closest to summer solstice. And so that is the issue here. If we align this 2 weeks prior to summer solstice, in other words, the sun is moving to the north, and then it turns around and goes back again. It crosses this line about 2 weeks before and 2 weeks after summer solstice. This alignment would mark out a span of time where we have about a month above this line. And sometime during that month, you're going to have a full moon. And so what you would do if you're using this as a calendar device would be to notice when the sun is in alignment with the head of the serpent, and that would mark the beginning of a month during which you would want to look for the next full moon. I'll leave it for you to read the article to get more detail here, but this is the observational component of what we take to be the interpretation of Serpent Mound and its usefulness to an ancient culture.